Okay, so make sure that you're doing those so you get points, and that's pretty much it. I feel like, well, thank you, Pete. Okay. Any other questions before we get started? On Thursday, I know there were a few people in class on Thursday. Actually, two people. It was Pete and Kayla were here on Thursday, last Thursday, and we did a bunch of problems, and it really it seemed like it helped those two students very well. So if you're not coming to class on Thursdays, I would really recommend that you come on Thursdays. If anything, just drop in, see what we're doing. But we did tons and tons of problems, and we just went over everything because a lot of this math is a little tricky. So just keep that in mind, that just because we technically don't have class, it doesn't mean when the virtual labs be posted. I don't know how, I'm still debating about even doing those. I just feel like there's a lot of other stuff that's going on. Yeah, so I'll let you know if I do post them, probably within the next week or two. It's only 2 labs, but like I said, in the meantime, and what I might actually do is that if I do post them on Thursday, we'll actually meet in the class and do them all together as a class. So it makes it a little bit easier. But as of right now, I'm thinking that we might not do them. We'll just do the pre-labs that I have you guys do. So I hope that answered the question. Okay, let me just. All right. Okay, sounds good. All right, cool. All right, I'm trying to. So far, I have so many things. I have your chat window. I got the participants window, and then I got the slides, and I got the recorder. All right, you guys able to see the slides? Okay. Okay, good. And I also want to open up the. Smooth draw. Excuse me. I've had this kind of a. I thought it was a small cold, like my son had a cold the week of spring break. It's like a typical cold that kids have, just a runny nose, whatever. And my other son got it, and it wasn't anything major, didn't have fever or anything. And then my wife and I got it, and it was a little different in us than how our kids had it. I had a little bit of a cough. After I didn't have fever or anything. And then after I was better, like a week later, I then started to get a headache for like 2 days, and then I was totally fine. And then after reading a lot about the coronavirus, they were saying that a lot of people, like most people, have very mild issues. And my wife and I are thinking that we might have actually had it in a very mild form of it. Because of the headache, that was a common thing, and then I'm having a little bit of a cough, where I have, so I don't know. And our kids might have had it, and it actually affects kids a lot different. It's not as bad, and it wasn't really that bad in us. So we're actually thinking that maybe we actually had a very mild form of it, which I'd be okay with, because that means my body has built up the antibodies for it. So once they get all the tests available, I'll test it to actually see if I have the antibodies for it. But we're actually thinking that we might have actually had it a few weeks ago, and luckily it was a mild form of it. Okay, well, that's it. Probably it's TMI for you guys. Whatever. I'm home with kids all day. I like to have adult conversations. Even though no one's talking back, I know people are there to hear me. Going stir crazy. I bet you guys are too. All right, let's see where we left off here. We finished. Okay, this is what we need to talk about. Yeah, electrolytes, I think is where. Okay, so yeah, we stopped at molality. All right, so that's where we stopped at molality. And I told you guys that really this in slide view so I have a pen. Okay, so I was telling you that molality you're really only going to see on the homework, and pretty much only on the homework, because it's not really a concentration that we use often. And this is moles of solute over the kilograms of solvent. So remember, the one that really is the important one is molarity. Molarity, which is the last few slides, which is moles per liter. Okay, this is kind of the main one that we use. We also did a percent by mass. You can also do by volume. It's the same thing, but instead it's volumes, but by mass. So it's grams of the solute over grams of the solution. And remember, the solution is the solute plus the solvent. Okay, so I just want to remind you that. Okay, for molarity, it's really whatever the volume of the liquid is. It's not really liter of a solution, because grams don't have really a volume, or the volume is very small. So if you say that you take X amount of grams of something and 100 liters, then you put the 100 liters on the bottom. So this grams of, so anytime you see gram of a solution, that's really, you have to weigh out the solute and the solvent. With molarity, you really just look at the liter or the volume of the liquid that you use. You don't have to add these, all right? You don't have to add them up. Okay, but molality is just the grams of the solvent over the moles, the moles of the solute over the grams of the solvent. All right, and here's just a few problems. I'm really not going to do them because the equation is pretty simple. You just take your moles, 0.253, and divide it by 1.75. Just remember that your solvent has to be in kilograms. So if it's given to grams, like here, you have to convert it into kilograms. If they give you grams, you have to convert it into moles. So that has to be converted to moles. That has to be converted into a kilogram. All right. All right, so I want to talk about electrolytes. So electrolytes is a substance that dissolves in water to yield a solution that conducts electricity. That's the important thing here. What makes something an electrolyte is the fact that it conducts electricity. All right, there's something, so basically if you take, and the way that they found this, I think they have a picture of it. Yeah, so here's a picture. So if you just have 100% water, this is just water, and you put this light bulb, so how this is working is the light bulb is plugged into the wall, and there are these two electrodes that are coming down. I actually have a video I'll show you guys. All right, and basically when if you have just water, electricity can't flow through water. So if you put in electricity, it can't actually travel through water, and the light bulb won't shine. I know a lot of people say you shouldn't have your hands wet if you touch an outlet, and don't drop a hair dryer in the bathtub because you'll get electrocuted. Well, it's not because of the water that is causing the electricity to actually travel. It's the ions. It's these ions in the water that electricity flows from. So it flows through the water via the ions. All right. If you do not have a charge inside of your water, so example, if you just have pure water, you can't have a current, an electric current. You have to have the ions inside of it. So our water in our sinks and our bathtubs and stuff have tons of ions inside of it. It's not just 100% water. So an electrolyte, this term of, I'll just go here since I'm having trouble writing it. So an electrolyte is a compound that dissolves in water and it ionizes so that it conducts electricity. So a salt of some sort, like sodium chloride, magnesium chloride, any of these salts, even acid, like hydrochloric acid ionizes in water. If these ionize, once they ionize, they start forming these ions. Water kind of, it goes around the ions. And now electricity is able to flow through it. All right. A non-electrolyte is still a compound that dissolves in water, but it does not ionize. Okay, so it dissolves in water, but it does not conduct electricity because it does not ionize. All right, it does not ionize. So an example of something that dissolves in water but is not composed of ions is sugar. Okay, and again, the way that you know if something ionizes is if it's an ionic compound. And how do we know if something is ionic? It has a metal and a non-metal attached to it. Metal and non-metal. That's what makes something ionic. Like all these have a metal and a non-metal. Magnesium's a metal, chlorine's a non-metal. Acid is an example of an acid where it still ionizes to H plus ions and Cl minus ions. Okay, but so if it ionizes into two ions, so we've learned about these, mostly if it's a metal, non-metal, unless it's an acid. So I'll add here also acids. Okay, or something called a strong acid, which we'll talk about in a second. Those ionize, so those are called electrolytes because they conduct electricity. Things that don't ionize but still dissolve in water are going to be a molecular compound. And remember, a molecular compound is something that has all covalent bonding, so it does not ionize, like sugar. Ethanol is another example. Ethanol, CH3, CH2OH. That it dissolves in water, but it does not ionize because I don't have a metal or a non-metal. It's not an acid. So these are examples where they dissolve in water, but they don't ionize. Therefore, they do not conduct electricity, so they're called a non-electrolyte. All right. So here's an example where they have sugar dissolved in the water, but the electricity can't travel through it because they don't have a charge. In order for electricity to travel through something, you have to have charged particles. So if you have an ionic compound in it, it will travel through it because you have charged particles. Okay. So I'm not going to do it in the equation. So let me show you this video that I usually show in class. So YouTube. Let's go to computer's taking slow. My computer for some reason takes really slow. This is typical. Of course, I'm not going to find it. Let's do electrolytes. Experiment. Huh. I know, there's this one guy. It's a great little video. On the computer at school, I have it saved on the desktop, so always. Too bad. You know, I'll find it on a break. I don't want to waste time doing this right now. Let's try one more. Let's just try this. I can't find it right now. All right, I'll find it on the break. Okay, sorry about that. Okay. This is solution preparations. I know I want to talk about... Yeah, and there's something I want to talk about which is not in here, but I want to talk about it. And it's the difference between a strong and weak electrolytes. All right, so let me insert a slide. Okay, so I want to talk about what's called a strong versus a weak. Actually, you know what? I find that this works better in writing. It like smooths everything out a little better. Strong versus weak electrolytes. Okay, so when we say strong versus weak, what we mean is how they ionize. So a strong electrolyte, is one that ionizes 100%. Okay, so an example would be like sodium chloride. When I throw sodium chloride into water, 100% of this will dissolve or ionize into Na plus ions into Cl minus ions. So if I have like a little beaker here, and I take my sodium chloride, which is a solid, and I put it in here, 100% of it turns into NaCl minus and plus ions. Okay? A weak electrolyte is one that partially ionizes. All right? Partially. So 100% of it won't ionize. Like, I'll take an example of acetic acid, for example. All right? Acetic acid is the acid in vinegar. Right, that's actually considered a weak acid or a weak electrolyte. So what happens here, so the actual formula is HC2H4O2. That's the actual formula. All right, but I'm going to do a shorthand for acetic acid for HACO. Okay, actually, sorry about that. It should be HOAC. That's the shorthand for it. So I don't have to keep writing all that out. Okay, and the ionized form of that would be like H plus and O minus AC. That'd be the ionized, because this hydrogen is the hydrogen that it pops off and becomes a plus charge, and then you get a negative charge on the acetate ion. That's the acetate ion. If you look at your polyatomic chart sheet, that's the acetate ion. Okay. So what happens when you throw acetic acid, so here's acetic acid, HOAC, all right, when I throw it into water, most of it stays as HOAC. The majority of it stays as HOAC, and a very few of the molecules actually break apart into H plus ions and OAC minus ions. Okay, but most of it stays all hooked together. So I have a very small amount of the ions, a very small amount of it. I don't have a lot of it. Where in the case here of sodium chloride, I have tons of it inside of the solution. The whole solution is ionized into a sodium ion and a Cl minus because it's a strong electrolyte. 100% of it ionizes. In this case, only maybe 5% of it actually ionizes, and the other 95% of it stays all bound onto each other. All right, so it still like dissolves, but very small amount of it actually ionizes. That's what is called a weak electrolyte, where it partially ionizes, or it doesn't ionize at all. Okay, so that's the difference between a strong electrolyte and a weak electrolyte. Any questions on that? All right, we also have things called strong acids and bases. We'll learn about this in a different chapter, but since we're talking about it, let's talk about it right now. A strong acid and base, and we also have what's called a weak acid and base. All right, so a strong acid, again, are ones that ionize 100%. There are only 6 strong acids. These are the 6 strong acids. I'll put SA for strong acids. They are HCl, HBr, HI, H2SO4, HNO3, and HClO4. These are the only 6 strong acids. Every other acid is considered a weak acid. All right, so I'm just going to give you the list of the 6, and then you know all the other thousands of them are considered weak. So acetic acid, like I said, is an example of one. Phosphoric acid is an example of a weak acid because it's not one of the 6. Okay, so pretty much every other acid is considered a weak acid. So these ionize 100%. All right, that's what makes it strong. It's not that it dissolves things very well. It's the fact that it just ionizes 100%. All right, and a strong base is the same thing. A strong base is also ones that ionizes, and there are 6 of those. Sodium hydroxide, potassium hydroxide, lithium hydroxide, and then it's the 2 A's. So strontium hydroxide, barium hydroxide, and magnesium. Actually, you know, guys, let me double check on that. Let me double check. Because I know one of them. Let's just do this. This might be calcium hydroxide. The strong acids. Oh, that's 3. I'm not going to include that rubidium. Yeah, strontium, calcium, and barium. Okay. So let me just correct this real quick. Strontium. This is calcium. Sorry about that. And this should be a 3. The perchloric acid is also a strong acid, but it's not as common. So this is called chloric acid. No, let's just get rid of calcium. Okay, so these are the 6 strong acids and bases. Everything else is considered weak. Okay, and again, these, all it means is that they ionize 100%. All right, everybody got those? Okay. All right, questions about that before we move on? And I'll find that video. It's kind of a cool video just to kind of show you how that works. Okay. Okay. So solution preparation. All right. What does this mean? I'm not pretty much going to go over that. But solution preparation is, let's say we have a stock. I'll actually go up to here. Let's say we have a, so when we do lab, all right, we usually have a bottle of acid for you guys already pre-made. All right, and we'll say something like this acid is 0.1 molar. All right, HCl. Okay, and we have a bottle of it. All right, let's say we have, I don't know, 500 milliliters of it. So we have 500 milliliters of a 0.1 molar solution of hydrochloric acid. Now, we have about 13 sections of Chem 101. So we don't just buy 13 500 mils of 0.1 molar HCl. We actually make it. What we do is we buy a stock bottle, so a big bottle of very concentrated hydrochloric acid. All right, and concentrated hydrochloric acid is about 12 molar hydrochloric acid. That's very concentrated. In fact, it's the highest concentration that you can get of hydrochloric acid. You can also get 14 molar of other acids, but this is very high concentration. And all we want is 0.1 molar. All right, and we'll buy like 5 liters of this. Okay, so a big big bottle of very strong hydrochloric acid. So when we have labs and we only want to make 500 milliliters of it, and especially 0.1 molar, we will take a small portion of this out and make our 0.1 molar hydrochloric acid solution. So I'm taking a small amount of this, all right? So I'm taking the small amount, and then I'm adding a lot of water to it. So imagine this is water. Okay, so I'm diluting it, right? So I'm taking a lot of water and I'm adding it to a very small amount of this, and I'm getting this. Okay, so all I have to do is buy one big bottle of this, and I can make as much of anything I want. I mean, obviously up to 5 liters, but if I'm only making 0.1 solution, I just need a very, very small amount of it. Okay, so this is what's called our stock solution, or our stock bottle. Okay, and it's the very concentrated stuff. So our lab techs have to do a calculation and figure out how much of this do I need, all right? How much of the concentrated HCl do I need, and how much water do I need to add all together and mix in order to make 500 milliliters of a 0.1 molar solution. All right, does that make sense? So what we're basically doing is a dilution. We are diluting it. And that's basically what this means, a solution preparation. All right, so how much of the solute am I using? Okay, how much water am I adding in the flask? All right, and then I shake it a few times and mix it up, and I figure out what my dilution is. Okay, so the formula, this is the formula. Now I'm going to give you a different formula that usually everyone uses. It's M1, V1. It's the same thing. It's a little different. M2, V2. All right, sorry about that. For some, like I said, that this program does that for some reason. I don't know why. Okay, there we go. So M stands for molarity. So the M is the molarity. And the the V is our volume. All right. So here it's the same thing. It's the molarity of the concentrated stuff, and it's the volume of the concentrated equals the molarity of the diluted times the volume of our diluted. Okay? So I'm going back to the last example. Let's go back to this example right here. All right? So I want to make 500 milliliters of a 0.1 molar solution, and I'm starting with 12 molar. Okay, so in order to do that, let's go to another screen. I think what I want to do is go to this. Okay, so I want to make, let me just draw this again, 500 milliliters of a 0.1 molar solution. And I'm starting with a very concentrated amount of 12 molar, 12.0 molar. So how much of this do I need, plus how much water do I need in order to make this? Okay, so my M1, my initial molarity, or what I'm starting with, is 12 molar. And I need to figure out how much of that I need to actually use, this quantity. So that little quantity is this RV1. And this equals what I want to make. So I want to make 0.1 molar, and I want to make 500 milliliters. I have to convert this into liters. Usually these are converted to liters. The reason is because molarity, remember, is moles per liter. Remember, molarity is equal to moles divided by liter. So that's my equation. M1 times V1 equals M2 times V2. I solve for M1. So M1 is 0.1 times 0.5, all divided by 12. All right, so let me do that. So 0.1 times 0.5 divided by 12. So I need to use, I'll round it up a little bit, so 0.004, let's do 2 sig-figs, 42, and remember this is in liters. Okay, now I'm going to convert this to milliliters just because of the fact it's such a small amount in liters. All right, so I'm going to convert it into liters. All right, so I'm sorry, milliliters. So I have to move this over 3 times. So it's 4.2 milliliters of my 12 molar HCl. So that means this quantity right here is 4.2 milliliters. All right, that's a very small amount. Like I told you, I had, how much of this we have? 5 liters of it. I have 5 liters. I need to take 4.2 milliliters. All right, so just to give you an idea of, so 5 liters, so if you take like a 2-liter bottle of soda, so if you think of those big plastic bottles of soda, it's like 2.5 of those. So imagine I have like 2.5 of those. And then 4 milliliters, all right, if you remember our 10 milliliter graduated cylinder, it's the very small ones, it's about half of that. So, I mean, I'm taking a very small amount of this, okay, and then I have to make this. So if I am using 4.2 milliliters of the 12 molar HCl, how much water do I have to add to this? So if you guys want to type that into the chat room, or if you want to unmute and tell me, how much water? So I got to take 4.2 milliliters of this, but how much water do I need to add in order to make this? Wait for someone to give me an answer. Are you guys still there? Or did I leave? Oh, there we go. Perfect. Justin, thank you. 495.8 milliliters of water. Right? Because my total volume is 500. I want to make 500 milliliters of it. Well, 4.2 milliliters of it is the hydrochloric acid. The remainder amount is the water. So basically, I'm taking a very small amount of this and adding tons of water into it because I only want 0.1 molar. I want a very dilute solution. Okay? So that's basically how you do a dilution formula, and it basically explains the process. So I'm going to take this amount of the concentrated stuff, add this amount of the water to it, and I should get this at the end of it. So that's basically what the lab techs do in our back room when we have labs and we have to use a certain amount of acid or something. They basically are using a stock solution because it's a lot cheaper just to buy one big bottle of this, and it lasts a very long time because, you know, again, we have 12 to 13 sections, so I need to make 12 or 13 of these. So I don't want to buy all those because it'd be expensive to buy each of them individually. We just buy one big bottle of the concentrated and make it. Okay? All right. So that's basically what that's all about. So let's get back to this. Okay. All right. So here's another problem. All right. Once you guys go ahead and do this, I'll give you guys a little bit of time to work on this problem. All right. All right. So we can do that. I like writing it out just to make it more like class. Okay. So our stock solution. So here you go. What volume of 12 molar a common laboratory stock solution? All right. So that's our stock. That's what we're starting with. 12 molar. Must be prepared to make 250 mils of 125. So this is identical to the last problem. You just have to change the numbers a little bit. All right, so M1 V1 equals M2 V2. All right, so 12 times, we're trying to find out how much volume that is, equals, and 0.125 times, and then convert this into liters, makes it a little easier. All right, again, sorry about these lines. For some reason in this it does that. So V1 is going to equal 0.125 times 0.25 divided by 12. Right, so you should get 0.125. And remember, your answer is in milliliters. I'm sorry, your answer is in liters. So you should get 0.002604. All right, and this is in milliliters. This is in liters. To convert to milliliters, remember you have to multiply by 1,000. So you move this over 3 places. So you should get 2.604 milliliters. I think Pete, you moved it over 100 places. or you multiply it by 100 rather than 1,000. All right, remember that there's 1,000 milliliters in 1 liter. All right, does that make sense, Pete? Other than that, it looks like you got it right. So how much? So okay, good. And then, so how much water? I don't know if it asked what volume. Yeah, all it says is what volume. But how much water would you add? Because I'll probably ask you that. So you should get in the habit of doing that, even though the problem isn't asking it. So yep, 247 point. I get actually 0.4. 204. I guess it's 2.6. So that's got to be 4. Yeah, 247.4. Yeah, good. All right. Typo. Okay. Yep. All right, good. So here it is, just an all out. Basically, they round up to 2 sig figs, so 260. Okay. The colligative property stuff, I'm not going to go over in class. This, you can watch the videos. These will just be a multiple question, a multiple choice type question. I don't really have much. I'm not going to do any of these equations. You don't have to worry about any of these equations. I think even on the videos, all I go over is like the definitions of them. Okay, so those you can do on your own. Okay, so really the only new thing that we learned in here is the electrolytes and the molarity problems. So why don't we take our break? I'm going to try to look for that video. Why don't we take a break, and when we come back around, I don't know, 5 after 11, we will start chapter 10. All right? Any questions or comments or anything? Okay. And again, if you guys, if it's easier just to say it than type it all out, that's totally fine. Just unmute yourself. Okay. All right.
The term electrolyte is a term used when talking about solutions with water as the solvent. We'll demonstrate the property of being an electrolyte with an electrical conductivity tester like this. Pure water does not conduct electricity.
I know, right?
I will put the electrodes of the apparatus into the beaker and the light.
This guy is like the quintessential, chemistry professor with the mustache and the beard and all that stuff. Yeah. But if you notice, so he's putting 100% pure water. All right, no, there's no ions or anything in there. It's just pure water. Cross-eyed. Is he cross-eyed? Yeah. Yeah, he's got his goggles over his glasses. It's total Colonel Sanders. Everybody needs a little chemistry. That'll be the joke. All right. All right. There it goes. Okay.
Lights very brightly. The dissolved material is called a strong electrolyte. As an example, here is a small amount of table salt. I'm going to add
I think he has a
just
ponytail
a little bit to the water and stir it up.
All right, so you put the sodium chloride in there. So first you just had pure water. Notice, so again, the light bulb, here's a light bulb. It's plugged into the wall, and it has these 2 electrodes. So in order to make the light shine, these electrodes have to have a current that goes through it. So if there's no current, it won't shine. So with the 100% water, it didn't do anything. But now that he put the sodium chloride in it, he now put the strong electrolyte in it. He now is going to have the ions in there, and you'll see that the light bulb will
As
shine.
it dissolves, the ions of sodium and chlorine, which are charged particles, go into the water, which will now allow the solution to conduct electricity. So the ionic substance, table salt or sodium chloride, is a strong electrolyte. The term non-electrolyte refers to a substance which dissolves in water but does not allow electrical conductivity. Here is some sugar, which I will dissolve in the water. As the sugar dissolves, the light does not light up. So sugar is a non-electrolyte. Some acids and bases are also strong electrolytes. Here's an example of some hydrochloric acid. Only a little bit in the water, and about 10 drops. Will allow the light to light up very brightly. So the acid is also a strong electrolyte, therefore it's called a strong acid. Acetic acid, on the other hand, dissolves but allows very little electricity to go through the water. See how the light bulb gives off much less light with a lot more acid. Thus we call acetic acid a weak electrolyte, and it is a weak acid.
All right. So I kind of showed you. Now I think it's hard to actually see that the light bulb was actually lighter, but if you go back, you'll notice that the light bulb is not as bright as with the strong electrolyte. All right. Okay. So, all right. Now it's fine. Chapter 10 slide. All right. So any questions? Any last minute questions on chapter 9? What I want you to do, I'll give you some time to do this, is I think we started talking a little bit. There's a, if you go to D2L, all right, and go under the handouts and download the solubility chart, this chart right here. Download the solubility. I have it right here. That's what it'll look like. We're going to start talking about reactions. Michael. Yeah, I know, right? My wife said to me yesterday, she said, "You wore that shirt for 3 days straight now." And I didn't even realize that. I said, "Yeah, I think you're right. I just, whatever clothes are nearby, I just put on." Yeah, right. Yeah, it's like our laundry, like we've had the least amount of laundry in the past 2 weeks between like my kids and I. My kids don't even dress anymore. They're just running around the house with their underwear. Anytime that they want to go out, they just throw on the closest thing that they have. Yeah, that's... Yeah, oh man, so many dishes. No kidding. No kidding. I saw a joke. It's so true. It's like I have to do social distancing from my refrigerator. I mean, it's so... you know, you eat when you're bored, so it's like, oh my god, I gotta. It's been insane. I also heard another joke from a parent saying that they said that my kids told me that they don't want the same teacher that they have while they're at home next year. That they hate their teacher, which is obviously them, their parent. Another parent says, I expelled my kids from homeschool. That's it. We're done. Quarantine calories don't count. Yeah, I wish. Oh, man. Oh, there's so many jokes going around, which is good. It's good. People are laughing. It's a whole new experience. Something totally different that we would never. I actually saw an interesting article. You know, they said, like, it was actually it was a joke, but it wasn't really a joke. It had two sets of scientists. It had on one side all of the doctors and the nurses and a microbiologist, and it had a picture of the Earth, and it had the Earth and a face on it, and the face had a frown, you know, saying everyone in the world is upset. And then there's another set of scientists, which are all the atmospheric scientists and all the ecologists, and they had a face of the globe that had a big smile on it, because I guess emissions are like down like 80% every single day. So because like people aren't driving anymore and all the traffic is gone, so they're actually saying it's actually really good. Yeah, you heard that. Yeah, that our emissions are so, and it's not just America; it's all over the whole entire globe. That that a lot of research is going to come out in the next year that just by doing a month of without driving or having high emissions might actually help global warming and all that stuff. Who knows? I mean, that's something that time will tell. I heard it was that the fish in the Venice Canal started coming back due to low. You got to be kidding me! That's crazy. And work from home. Yeah. I think it'd be great to finally maybe find a way, because it reduces traffic, or like you have to go to work every other day, and then at work at home on 2 days. I've heard that. They've also shown in rural areas that all the animals, all the wildlife is coming down from the mountains and are hanging out on the streets, are eating the flowers and stuff on the streets, and there was a show I think on Discovery Channel called I can't remember the exact title, but what the Earth would be like without humans, and it basically showed in the first few months all the wild animals would all come out from the woods, and basically start exploring wilderness sites. Yeah, mountain lions in yards and towns, exactly. So, all the animals, like, finally these humans are finally gone. Let us have our world back. So so it's interesting in that way to actually see all that happening. I'm gonna pull this up. You guys are typing faster. A little bit of light in the dark, exactly. That was very melodramatic of me. No, what was head? Mountain lions. Yeah, deer. Yep. Everything. Really? That's interesting. I'd be interested to find that article. So all the monkeys who were fed by tourists in Thailand are coming into town in groups of like 80 and fighting. Holy cow, yeah. Oh man, I'm gonna have to check that out. So in Thailand, the monkeys in Thailand. That's interesting. Yeah, that's a good point, because all the animals who are relying on people now don't have that. Okay, with that said, so if you guys downloaded that, let's get to the reaction. So this chapter is about reactions. We're going to start looking at reactions now. So this is kind of a big chapter, a lot of more challenging stuff in this chapter. All right, so recognizing chemical, let me just see my notes real quick. I'm going to go more by my notes. All right, so a chemical change or a chemical reaction. So a chemical reaction caused by atoms, but do not cause either the creation or the destruction of atoms. So that's kind of important to remember that. Remember, any reaction, whatever atoms you start with here, all right, you end with the same types of atoms. All right, so if you start with iron or oxygen or something, sulfur, in your final product, you also have to have iron, oxygen, and sulfur. They're just rearranged. All right. So in type A, or in reaction A, it's showing you that you have iron. All right, iron, the element iron, and you're adding it to oxygen, and you get rust. So you get iron oxide. All right. So that is a reaction. All right. So notice, yes, I still have iron and oxygen, but it's in a different form now. All right. Here's a cake. They're just showing you that a cake is also a chemical reaction with like the baking soda and the yeast and all that stuff. All right. Oh, yeah, this is just kind of showing you the difference between a physical change and a chemical change. I think we all know the difference between physical and chemical. Like if you look at A, between A and B, that's a physical change because we have the reds and the greens attached. We still have the reds and the greens all attached. All right, so it's going from like a liquid or a solid into a gas. All right, but here we actually have a rearrangement. So from A to B is a chemical change because the A's now are combining with the other A's and the B's are combining with the B's. Same thing, C is also a chemical change with respect to A. So that's pretty much all what they're showing you there. Okay, so when you do a chemical reaction, this is just all the nomenclature. You have ammonia, you're taking ammonia, you're adding it to hydrochloric acid, and your product, so the arrow implies yields or forms, and then this is the product. So here's our product side, and then this side, we either call it a reactant side or you can call it your starting materials. Okay, so just kind of some naming for it. And left arrow. Okay, we talked about that. Remember the diatomic molecules. All right, these are the diatomic molecules. This is just to remind you. Remember, they have no fear of ice cold beer. All right, so the diatomic molecules, those are the molecules that exist in pairs. All right, like if we just talk about iron itself, it's just iron. It's a single iron atom. That's iron. If you talk about, I don't know, chromium, it's just chromium. All right, but these are the 7 diatomic molecules. This one we're not going to worry too much about. The phosphorus, we won't see it too often, but phosphorus too, in the elemental form, actually exists as 4 of them. But remember, they have no fear of ice, cold, beer. All right, so like oxygen, when you talk about the element of oxygen, it always exists as pairs. Okay, that's just kind of what it's reminding you of. So here's an equation that actually has more information. Now it's giving you all of the states of matter. So you can either have a gas, you can have a liquid, you can have a solid, but you can also have something called aqueous. All right, aqueous just basically means it's a compound that is ionized in water, or it's dissolved in water. So like you can have sodium chloride in the solid form, which is actually salt, but if you take it and you dissolve it in water, you have sodium chloride in the aqueous form. It's still sodium chloride, it's implying that it's dissolved in water or ionized. So that's what that aqueous implies. So here's kind of an equation just to kind of show you in its full glory. So you have all the reagents, hydrogen, oxygen, and then the product. And then you have all the states of matter. So you have the gas, and the liquid. But then we also have these whole number coefficients. So right here you don't have a number, but that actually is a 1. And then you have another 1 here. This is in our balancing of the equation. We talked about this when we did the lab, the rocket lab. We did balancing the equation. I just kind of briefly showed it to you. Now we're actually going to do more. We're going to go more into it. But basically, a reaction is if you start with, let's say, 6 atoms on this side of the equation, you have to end up with the same number of atoms on the other side of the equation. So if you start with 6 atoms, all right, you have to end up with 6 atoms on the other side. Okay, that's a fundamental rule of science. Whatever that matter is neither created or destroyed. It's just rearranged. So it's not destroyed. If you start with 6 iron atoms, you got to end with 6 iron atoms. Like, for example, if this equation was not balanced, we would have H2 plus O2 gives you H2O. All right. Now I have 2 hydrogens here, and I end up with 2 hydrogens here. I have 2 oxygens here, but notice I only have 1 oxygen on that side. So that's 2, that's 2. There's 2 here, but only 1 here. All right. That goes against the fundamental rules of science. If I start with 2 oxygens, I better have 2 oxygens on the other side. So in order to make this work, you have to balance the equation. All right. And the way you do that is you put whole number ratios in front of the equation. So if I wanted 2 atoms, all right, obviously it means one of the oxygens over here. So remember, oxygen, there's a structure of oxygen, plus here's a structure of hydrogen. These 2 hydrogens pair up with one of the other oxygens to form H2O, and I have an oxygen left over. Well, what happens to it? Well, it pairs up with another equivalent or another mole of hydrogen. All right, so for every 1 oxygen molecule, you form twice the amount of water molecules. So you have to show that in the equation by saying you need 2 hydrogens for every 1 oxygen to form a total of 2 moles of water. Okay, so now if you look, we have 4 hydrogens here, 2 oxygens here, and now on this side, because I formed 2 water molecules, H2O and an H2O, I now have a total of 4 hydrogens, and I have a total of 2 oxygens. So it's balanced. I'm showing where all of the atoms are going. And that's basically what balancing equations are. Okay. So here are some rules. I'm going to go, let's see, change the coefficients by changing, the compounds by changing the coefficient of the element. Right. So if you it's the number in front. Like for example, if I had H2 plus O2 forming water, you know, it'd be really easy to say, you know what, I'm just going to put a 2 there, and now everything's balanced. Look at that. I balanced everything. That's great. I got 2 of everything. Well, you've just changed what your compound is. You can't just change your compound, all right? Because now I have hydrogen peroxide, all right? So you can't change a subscript. You have to change a coefficient. So a coefficient are these whole number right in front of our molecules, okay? Another rule I want to talk about, and I think I talk about in the videos, is that when you're doing balancing, you want to start with the molecule that has the most number of atoms first, and then start with the atoms in the highest amount. All right, and I'll show you on these problems on how to do it. All right, polyatomic ions, you want to treat as one ion. Rather than trying to balance each individual atom, which will become a nightmare, balance a carbonate atom. So if you have like MgCO3 2 on this side, and then I don't know, you have, I don't know, let's say Fe2CO3 3. Don't try to balance each individual atom. Balance the whole ion. So if I have 2 of them here and 3 of them here, you have to find the lowest common ratio between them, which would be 6. So that means I got to put a whole number 3 here to make 6 carbonates, and then I put a whole number 2 there in order to get 6 of the carbonates. Don't try to balance, you know, I have 3 carbons here and only 2 carbons here, and 6 oxygens here and 9 oxygens here. It'd be a nightmare. What you want to do is balance the whole thing, and I think we'll see a few of those problems. Track your numbers. Okay. So if you do not have polyatomic ions, notice here I have the polyatomic ions. I have a phosphate and a phosphate. So I have 2 of the same things on this side. But in this case, I don't. I have a phosphate and I got a phosphorus with chlorines. Okay? So the trick is, so in this case, I'm going to balance each individual atom. Okay? So I told you that the rule is first start with the molecule that has the most number of atoms in it. Okay? So this one has 6 atoms in it. This one has 3. This one has 7, 8. This one has 8. All right, and this one only has 2. So I'm going to start balancing this molecule here because this has the most number of atoms. Then you start with the atom that is in the highest amount. So I'm going to start balancing the oxygen. That's where I'm going to start. A lot of people might want to start with the phosphorus or the chlorine. You can. In some cases, it works well, but other cases, I find if you just do this, it works a lot easier. So I have 4 oxygens here, so I need to get 4 on this side. So I'm going to put a 4 right there. Okay? So now I have a total of 8 oxygens there and 8 oxygens there. Okay? Now I'll go to the next atom, which is hydrogen, or our highest amount, our next highest amount, which is hydrogen. There's 3 here, plus I have another 1 here. Okay? So I'm going to, so I have 2 things here. And here I have a total of 8 on this side. So how do I get a total of 8 on the other side? Well, I've got 3 here, all right, and so that means I need to get 5 of these. So I'm going to put a 5 in front of the hydrogen there. So now I have a total of 8. 3 plus another 5 is my total of 8, which is 4 times 2. Okay. Then I go to my next atom in the same molecule, which is phosphorus. I have 1 here. I have 1 here. So that's balanced. Then I go to the next molecule that has the highest amount of atoms, and I do the same thing. So in that case will be the PCl5. Start with the chlorine, 5 chlorines, and since I have the 5 here, that's already balanced out. So it looks like everything is balanced. And if you want to check, you just check. So I have 1 phosphorus here, and I have 1 here. I've got 5 chlorines here, and now I have 5 chlorines here. 8 hydrogens, and the 3 plus the 5 is 8, and 4 oxygens and 4 oxygens. So you always know if you have the correct answer, because if everything balances out, then you know you did it correctly. Okay? So the trick is, like I said, start with this molecule first because it has the most number of atoms. Then start with the oxygen because it has the most number of atoms within the molecule that has the most number of atoms. And then you go down from there. All right? So any questions on this one or how to do that? Okay. When you have polyatomic ions, meaning you have the same ions, I'm not going to balance each individual phosphorus or oxygen. I'm going to balance the whole entire phosphate group. Okay? So again, start with the molecule that has the most number of groups in it. All right, so this has 3, because it's a calcium plus 3 of these. This one has 4, 3 sodiums and 1 phosphate. This has 5, 3 calciums and 2 phosphates. So again, I group this as a whole group. All right, so I'm going to start here, and then so I'm going to start with this molecule because it has the most number of atoms. Okay, and then I'm going to start with the calcium because that's the highest amount. So there's 3 calcium here, so I got to put 3 on this side. Then I go to the phosphate and balance the phosphate, and I got to put a 2 right there. Okay, then I go to the next atom that has the most amount, which looks like it's the sodium phosphate. So the phosphate is the next one I balance. So there's 6 now of sodiums. So I got to put a 6 right there. And then that means I've got 2 phosphates, which I have. Next is the chlorines. I have 6 chlorines and 6 chlorines. So everything should be balanced. 3 calcium, that's balanced. 6 chlorines and 6 chlorines. 6 sodiums, and 2 phosphates and 2 phosphates. Okay? So it's balanced. So again, what does the balancing mean? That means I need 3 times the moles for every 2 moles of the sodium phosphate. So this is a 3-to-2 ratio. And again, it's based on moles. So if I have 3 moles of calcium chloride, I need to make sure I add 2 moles of sodium phosphate to it. And again, if I want to find out how many grams it is, I take the number of moles and multiply it by the mass of the sodium phosphate, and I can figure out how much of this I need. All right, so in doing this reaction, in order to have a complete reaction, I want to make sure I do it in a 3-to-2 ratio. If I do a 1-to-1 ratio, I'm not going to get a complete reaction. In this case, it's a 1-to-4 ratio. I need 4 times the amount of water, moles-wise, as far as my phosphorus pentachloride. Okay? So that's kind of what those numbers are telling us. Okay, now, the third type of problem you'll get is this type of problem. This is a combustion reaction. Combustion, which we will learn about this type of reaction. It's very characteristic. It's basically a hydrocarbon of some sort. This is called hydrocarbons. I'm sure you guys have heard of the term hydrocarbon. A hydrocarbon is basically just a molecule that is composed of carbons and hydrogens. All right, pretty straightforward. All right, and you add it to oxygen and you burn it. You basically form carbon dioxide and water. Okay, so that is a combustion reaction. For these types, what you want to do is just start at the carbon, balance your carbon, your hydrogen, and you're going to end up balancing your oxygen last. Sometimes you might have to use a fraction. I don't remember if you have to do it in this case, but we'll go through it and see. So I have 4 carbons here, so I want to put a 4 here. 10 hydrogens here, so that means a 5 there. Okay. And then so as far as oxygens, I have 8 total oxygens here plus another 5. So what is that? 8, 9, 10, 11, 12. So that's 13 oxygens. Okay. Well, how do I get 13 oxygens? I can't put a 13 here because that would be 26. Right? So what you do is a fraction. Obviously, it has to be a fraction amount. So I'm going to do a fraction. I'm going to put 13 halves right here, right? Because it's actually 7.5. If you take, 6.5. All right? I need 6.5 oxygens. Well, how do you get a half of an oxygen? That's impossible. I can't have O. I have to have O2. Okay? So in doing a combustion reaction, this is the trick that you want to do. So put 13 halves. However, you can't have fractions here because you can't have a half of an oxygen. So if you remember in algebra, in order to get rid of fractions, you multiply the whole equation by this lower number. So I'm going to multiply this whole equation by the number 2. All right? And you basically distribute that 2 throughout all of the numbers. Right? So your final balanced equation is going to be 2C4H10 plus, now my 2's cancel. I get 13O2 gives me 8CO2 plus 10 H2Os. Okay? So these are the three types of equations that you'll see, that you'll come across. Either one where nothing matches, all right, and you start with the highest number, or you have polyatomic ions, which you balance the polyatomic ions, but it's the same rules as you use up here. Start with the most, and then you work down from there. And then finally, you go to the combustion one, which sometimes you'll have to do this trick, but other times you might not have to. It might, if this turns out to actually be a whole number, so instead of 13 you get like 14, then you can just put a 7 there, and you're good to go. You don't have to do this trick. Okay? All right. So here's just some more balancing stuff. Just kind of skip that. Okay. Give me 1 second. I'll be back in 1 second. I have to go grab something. What's going on? There we go. You guys hear me? Just hit yes if you can hear me. Something weird happened. Okay, good. All right. Okay, chemical reactions. This is where we're going to start getting into, if you take A, you get B, and you kind of predict what products are. All right. The first, okay. So this is the first reaction we're going to talk about. I don't know how much time we have. We only have about maybe 10 more minutes, so I'm not going to go too much into it. But tomorrow we are going to pick up right here. I'm going to spend a lot of time on this. All right, there are several different types of reactions. One of the ones that we're going to be learning about right now is called a double replacement or a precipitation reaction. All right, so this type of reaction is a type of what's called a double replacement. I think book either calls it replacement or a displacement. Yeah, it's right here, a double displacement, but it could be called a replacement too. Displacement reaction. There's also a video I want to do, but I don't know if I'll have time to do it. But I kind of like this picture. Okay, so this is basically what the reaction is. Notice I have two beakers here. I have beaker 1, a beaker 2. In beaker 1, I have sodium iodide. In beaker 2, I've got lead nitrate, lead 2 nitrate. Okay, notice they are clear, colorless, aqueous solutions. If you take lead nitrate, which is a white solid, and throw it into water, it ionizes. All right, and then they're kind of showing you all the ions here. If you take sodium iodide and throw it into water, it also ionizes. So I have two clear solutions. They look like they're just water, but they aren't. They actually have the ions floating around. Okay, these are aqueous solutions. Remember I talked about aqueous as the other state? Notice we have sodium iodide, AQ, meaning it's aqueous, lead nitrate, aqueous. Because the water is not doing a reaction. It's just kind of it's the medium that's holding these compounds. Okay, because if I were to take salts and just I put them on top of each other, they wouldn't do anything. They actually have to be ionized and all dissolved in order to have a reaction. So I have sodium iodide, aqueous, and then I have lead nitrate, which is aqueous. Two clear, colorless solutions. But when I mix them together, look at this. I get this yellow solid forming. This is actually a solid. All right? Amazingly, as soon as I pour this in, it's like yellow solid. Like this is like witchcraft, right? Like how is that even possible? How do I get this solid all of a sudden? And on top of it, it's yellow. Okay? And eventually, you can let it float at the bottom. So I have this yellow solid. So what the question is, what is that yellow solid? What is this? Okay, now in the slide it tells you, but how can you predict this? All right, how can you predict I'm going to form a solid? And this solid is called a precipitation or a precipitate. Okay, precipitation. When we say it's precipitating outside, it's like raining or snowing or something. That just means that something is falling out of the solution that isn't in the same state as what our solution is. So like when it rains, right? Our air, our atmosphere, is all gas. But when we have water falling out of it or snow, that is a precipitation. It's falling out of the solution. Our solution is the gas, is air, and the precipitate is sorry, excuse me, guys. is the rain or the snow. Okay, so in this case, our solvent is the water, and what's falling out of it is a solid. All right, so let me just show you the video, and then we'll call it from there. Hopefully, it'll be quicker to find it this time. Just so you know, I don't watch all these gaming videos. My kids do. All right. So I don't know if you guys watch Unspeakable and Preston and all that stuff, but my kids love to watch. Kayla said, sure. I would love to play Fortnite with my kids. It's just there's so much going on. I don't have time to learn it. As a kid, I used to be all totally into gaming, but nowadays. All right. Let's see where this video is. I'm having a hard time finding these videos nowadays. All right, we'll just do this one. I don't want to keep looking for. Okay, I'm gonna put it on mute, so I'll talk about it. So, all right, there you go. That's it. So it's the same reaction. So initially in here, clear, colorless solution. Let's see what he says. So this is the lead nitrate inside of here. And then as soon as he adds the potassium iodide or the sodium iodide, what did you say, Mike? You can handle Fortnite. I mean, I understand it. It's just, it's the controls. It's learning it. I mean, on the iPad, I find it annoying. It's hard to do on the iPad. My son uses the Xbox, which is annoying. And then my computer is so old, I can't get it on my computer. So, all right. So anyways, there you go. So the question is, what is this white, this yellow solid? All right. Let's actually do a few of these. Let me actually just show you a few of these. This lab, it's too bad that we aren't doing this lab because it's a fun lab. You actually see all the solids form. I'm having such a hard time finding stuff. Let's do this one. Not it. Just basically. All right. So here's an example where you take like silver nitrate and sodium chloride. You form a white precipitate. Okay. Now, and so if you looked at that reaction, we'll just do another one. So if you look at this, notice this is part of the precipitate. Was this going to be a chemical? Yeah, yes, it was. So this is our solid, our precipitate, and this is still in the solution. It stays ionized in the solution. All right. So what we're going to start seeing is that if you take these, we get two different products. One of them, it turns into the solid, and the other one stays ionized in the solution. All right, let me get it. That's a cool one. So that one has silver chromate in it. This was probably like copper. Yeah, all the copper compounds get this. It's kind of like a gelatinous form to it. Let's see if we can find other ones that are. There's calcium chromate. I just want to show you the reactions. I'll talk about that. All right, so here it looks like what would it dissolve in there? So it looks like sodium carbonate. All right, so you wait out the sodium carbonate, put in water, he's mixing it, it eventually dissolved. All right, he has a certain amount, and then here is the calcium chloride or whatever it was. What does he have? Calcium chloride and sodium carbonate. And as soon as he mixes the two together, you form a precipitation. And again, one of the products is the precipitate. The other product stays in the solution. So there's a joke. If you're not part of the precipitate, you're part of the solution. Kind of play on words. Chemistry jokes. I'm sure you guys miss my chemistry jokes. I feel like I haven't said them in a while. All right. Okay, so that's kind of what this part is going to be. So let's go over this solubility list. So basically the question is, how can you predict what the solid is going to be? All right, I've got lead iodide, I've got lead nitrate. All right, how do I know what this is? All right, in this case, it's telling you it's lead iodide, but that's what we're going to learn starting tomorrow, because I think we're about time. Okay, so here's a solubility chart. This kind of helps you predict what stays ionized and what forms solids. Okay, so that's kind of, this chart is probably about 90% of the rules out there. There are tons of charts, but we're just going to look at some of the common ones. Okay? All right, so any questions before we take off? That's pretty much it for today. We don't have much more time. You guys have any questions or anything? All right. If there's no questions, I will see you guys tomorrow. Yep, no problem, Pete. Yep, Michael, no problem. Yep, Andrew, yep, see you there. Emmy, no problem.